Hello, and welcome to my tutorial on 2D elastic collisions. So what I'm going to do first is write down the solution to the 1D elastic collision that I previously solved on the chalkboard. So, one-dimensional elastic collisions. And the solution we came up with before was V1F is equal to M1 minus M2 divided by M1 plus M2 times V1I plus 2M2 over M1 plus M2 times V2I. And V2F, if we plug this into that equation, that I left off last time when I was deriving this on the chalkboard, we'll get 2 M1 over M1 plus M2 times V1I plus M2 minus M1 over M1 plus M2 times V2I. So that was, so these are the solutions for the final velocities of the two particles after the collision. Now let's take a look at 2D, two-dimensional collisions. Okay, again, we're going to have two particles. Let me draw this out here. And they're going to have some initial velocity, but now their initial velocities are going to be two-dimensional. So let's just draw some velocity vectors here. Let me add this way. Okay, so we'll have some velocity. We'll have some velocity. And we'll call this one particle 1, M1. This one particle 2, M2. And we'll have some V1 initial, it's a vector, and some V2 initial, and it's a vector. Okay. Now, the way we would write this, big V1 initial as a vector, has two components now since we're dealing with two dimensions. And we have V1 initial in the x direction, I hat, plus v1 initial in the y direction, and that's j hat. Now we have v2i equals v2 initial in the x direction, I hat, plus v2 initial in the y direction, j hat. And that's what our two velocity vectors look like. Now, since we're dealing with two dimensions, these particles are not going to be restricted to the x-axis, and they will have some position vector associated with them as well. So, position of this particle is r1, and the position of this particle is r2. And again, the position vectors themselves are two-dimensional, so r1 is equal to some x1 in the I hat plus some y1 in the j hat. R2 is equal to some x2 in the I hat plus some y2 in the j hat. Okay. Now, as before, the two particles will collide and move off with some final velocity, and we'll end up with some final velocity Vf, V1f, which is equal to V1fx in the I hat, plus V1fy in the j hat, and our final velocity for the second particle will be some V2f in the x I hat direction plus V2fy in the j hat direction. And that's how we would write this down. Now, solving this, we go through the same steps as we did before. So we use conservation of momentum. Which dictates that the final momentum, the total final momentum, is equal to the total initial momentum. In this case, we have two dimensions, so let's write down the momentum, initial momentum for the first particle. Since the initial momentum of the system is equal to the initial momentum of particle 1 plus the initial momentum of particle 2, which is equal to m1 v1I plus m2 v2I And the final momentum of the system is equal to the final momentum of particle 1 plus the final momentum of particle 2. And again, we will write this as m1 v1f as a vector, m2 v2f as a vector. Now, applying our conservation of momentum condition, we have that m1 v1f plus m2 v2f is equal to m1 v1I plus m2 v2I. However, our velocities have 2 dimensions, so we have to take that into account. So let's plug in our velocity vectors here. So v1f, m1 times v1f x, the I, plus v1 fy in the j, plus m2 times v2f x in the I, plus v2 fy in the j, and that's equal to, just write it down here, m1 times v1I in the x plus v1I in the y plus m2 times v2I in the x plus v2I in the y. Okay, so now what I want to do is I want to collect my I hats and j hats on both sides. So we have m1 v1 fx plus m2 v2 fx in the I hat plus m1 v1 fy plus m2 v2 fy in the j hat is equal to m1 v1 I x plus m2 v2 I x in the I hat plus m1 v1 I y plus m2 v2 I y in the j hat. Okay. So everything in the I hat is equal to everything in the I hat, and everything in the j hat is equal to everything in the j hat. So this gives us 2 equations. And we have m1 v1 fx plus m2 v2 fx is equal to m1 v1 ix plus m2 v2 ix and m1 v1 fy plus m2 v2 fy is equal to m1 v1 iy plus m2 v2 iy. And much like we did before, we'll rewrite these so that we'll have dimensionless ratio of proportionality. So subtracting m1 v1 ix from both sides gives us m1 times v1 fx minus v1 ix, and subtracting m2 v2 fx from both sides gives us m2 times v2 ix minus v2 fx. Doing the same for the second equation. We have m1, subtracting m1 v1 iy from both sides gives us v1 fy minus v1 iy, and that's equal to m2. Now subtracting m2 v2 fy from both sides gives us v2 iy minus v2 fy. And so now we can build two ratios of proportionality. If I divide both sides by m2 on this top equation, this first equation, and divide both sides by v1 fx minus v1 ix, we get what we had last time. Of course, now we have a second equation for the y direction. So m1 over m2 is also equal to 2iy minus v2 fx, sorry, fy, divided by v1 fy minus v1 iy. So now we have two equations that we can extract from our conservation of momentum condition. So before we continue on to the conservation of kinetic energy, let me be very explicit about what we know and what we don't know here. So, we know the initial position of each particle, x1, y1, x2, y2, and we know the initial velocity. We assume we know the initial velocity of each particle before the collision. So that would be v1 ix and v1 iy, v2 ix and v2 iy. What we don't know are the final velocity components, v1 fx, v1 fy, and v2 fx and v2 fy. So that's what we're trying to solve for. So technically we have 4 unknowns. 4 unknowns. Now these are the components for the velocity vector in Cartesian coordinates. v1 fx, v1 fy are the 2 components in 2 dimensions for the final velocity vector, and v2 fx and v2 fy are the 2 components of the final velocity vector for the second particle in Cartesian coordinates. Now we can either know the components themselves individually, or we can know the magnitude of the velocity and the angle with respect to our coordinate system, so the direction, and then we can decompose that into our Cartesian components. And just a reminder of how to do that, let's just assume we have some velocity vector v, and this is the x-axis, and here we have the y-axis, and we have some angle theta, and we know the magnitude of the velocity. So we can easily find the components of that velocity vector by looking at the cosine of theta for the x direction and the sine of theta for the y direction. Now, remember, the cosine of theta is the side adjacent over the hypotenuse, and the hypotenuse here is just the magnitude of the length of this vector, which is the magnitude of our velocity vector. And so we can write Vx and Vy. Vx is just equal to the magnitude of the velocity vector times the cosine of theta, and Vy is just the magnitude of the velocity vector times the sine of theta. Okay, so we still have 2 unknowns, theta and the magnitude of the velocity for each final velocity. So 4 unknowns, and we can either represent them as the components of this velocity vector, or we can represent it as the magnitude and the angle with respect to our coordinate system, and then decompose them into the components if we wish. So again, just to rehash, we know the position of each particle, so that would be the components x1 and y1, x2 and y2. We know the initial velocity components for both particles, v1 ix, v1 iy, v2 ix, v2 iy. So all those are known, technically 8 knowns, but 4 knowns when it comes to solving for the final velocity using the conservation of momentum and the conservation of kinetic energy. And our 4 unknowns are v1 fx, v1 fy, v2 fx, v2 fy, or the magnitude of v1 and theta 1, and the magnitude of v2 and theta 2. And then we can decompose them. All right, so now let's move on to the conservation of kinetic energy. All right, now let's take a look at the conservation of kinetic energy. Conservation of kinetic energy, which basically dictates that the final kinetic energy of the system is equal to the initial kinetic energy of the system. Now, the initial kinetic energy of the system is just the sum of the individual kinetic energies of each particle. So, the kinetic energy of particle, initial kinetic energy of particle 1, plus the initial kinetic energy of particle 2, and the final kinetic energy of the system is equal to the sum of the final kinetic energy of each particle in the system. So, the kinetic energy of the first particle, the final kinetic energy of the first particle, and the final kinetic energy of the second particle. Now, as you should recall, kinetic energy is just 1/2 m times the magnitude of the velocity vector squared, and the magnitude of the velocity vector squared, one way to describe it is the dot product of the velocity vector into itself, vxi plus vyj dotted into itself, vxi plus vyj. And now we can just simply expand this the way we normally would algebraically, keeping in mind that the dot product of I into itself, the basis unit vector I into itself is 1 by definition, and the dot product of the basis unit vector I into the basis unit vector j is 0, since they are orthogonal, which means that they have a 90-degree angle between them. And so the dot product between those two basis unit vectors would be 0 by definition, which eliminates the cross terms. So this would just give us vx squared plus vy squared. Now, another way to look at that would be just utilize the Pythagorean theorem here. Remember, this is a right triangle that we're looking at with sides vx and vy, and hypotenuse v, or the magnitude of our velocity vector. And so a squared plus b squared is equal to c squared, simply translates to, I'll just write it down, vx squared plus vy squared is equal to the magnitude of the velocity vector squared. Okay? So now going back to our conservation of kinetic energy, we can rewrite this. Now, writing the individual kinetic energies for each particle. The individual kinetic energy, excuse me, now the kinetic energy for particle 1, the initial kinetic energy for particle 1 is 1/2 m1, the magnitude of the initial velocity for particle 1 squared. The kinetic energy, initial kinetic energy for particle 2 is equal to 1/2 m1, m2 second mass v2I squared. Now we can rewrite this as 1/2 m1 times v1x squared, v1ix squared plus v1iy squared. So v1ix squared plus v1iy squared. And this one is just 1/2 m2 v2i x squared plus v2 iy squared. And we know these. We know the components of our initial velocity. Well, we assume we know the components of our initial velocity. So the initial kinetic energy is just some value, and it's known. We can calculate it. Now the final kinetic energy of each particle, K1 final, is equal to 1/2 m1, the magnitude of the final velocity for particle 1 squared, and the final kinetic energy of particle 2 is just 1/2 m2 magnitude v2f squared, and again writing it in terms of its components, m1 times v1fx squared plus v1fy squared, and this one is equal to 1/2 m2 v2fx squared plus v2fy squared. And now these four are unknowns. These four variables are unknowns. v1fx, v1fy, v2fx, v2fy. These are our unknowns again. Okay, now applying the conservation of kinetic energy condition. We look at the sum of the final kinetic energy of particle 2 and particle 1. And so that's just 1/2 m1 v1fx squared plus v1fy squared plus 1/2 m2 v2fx squared plus v2fy squared is equal to the initial kinetic energy of the system, 1/2 m1 v1ix squared plus v1 iy squared plus 1/2 m2 v2i x squared plus v2 iy squared. Okay, and there's a common factor of 1/2 between all of these terms, so we can cancel that out. And now collecting or like terms with respect to mass and velocity. So I'm going to subtract this from both sides and factor out m1. So that just gives us v1fx squared plus v1fy squared. Now it's minus this, minus 1ix squared minus v1 iy squared is equal to, now I'm going to subtract this from both sides and factor out m2. So basically a symmetrical operation here. There's some symmetry. v2ix squared plus v2iy squared minus v2fx squared minus v2fy squared. And in the same fashion that I wrote down dimensionless ratio of proportionality for momentum, I'm going to write down our dimensionless ratio of proportionality for our kinetic energy, much in the same fashion that I did for the 1D problem as well. So m1 over m2 is equal to, just divide both sides by m2, and now I'm going to divide both sides by this whole thing right there. So v2ix squared plus v2iy squared minus v2fx squared minus v2fy squared divided by v1 fx squared plus v1fy squared minus v1ix squared minus v1iy squared. So again, there's some symmetry there. You look at these dimensionless ratios of proportionality we derived from our conservation of momentum equation. And remember, it gave us 2, so we have 2. But the kinetic energy condition only provided us with 1. Okay, so we have 4 unknowns, but only 3 equations, our 2 from momentum and our 1 from kinetic energy. So how do we solve this? Well, there's a way we can do it if the point of impact is just that, a point where, or a flat surface, where an impulse can only be produced along one direction, or we can utilize a trick, and that is to rotate our coordinate system along the direction of that impulse, thereby eliminating the impulse in the orthogonal direction, if there isn't any, which we assume there's not if we assume that we can resolve our impulse down into a single direction. That we can define and calculate. So I'll be more explicit about that as we go on and we take a look at the situation between 2 circles or spheres in particular, and rotate our coordinate system along the line that joins the center of both of those geometric objects. So circles and spheres Okay, now before I continue, I'm going to be very explicit again about what we know and don't know. Again, we have 2 equations generated by our conservation of momentum condition. And we have a third generated by our conservation of kinetic energy condition. Okay. And we've got 4 unknowns. So v2fx, v2fy, v1fx, v1fy. We know v1ix, v1iy, v2ix, v2iy. We know m1 and m2. So 4 unknowns, but 3 equations. So how do we solve that? All right. So first of all, let's take a look at what happens when 2 circles collide. So I'm going to draw this out. So some random orientation. Okay, and let's say they collide at that point right there. Okay, now we also know that's about right. Good enough just to represent what we're doing here. So we know the position of the centers of these 2 circles with respect to some coordinate system. So let's call this mass 1 and this mass 2. So we know R1 and R2. R1 and R2. Okay. Now, if we look at the point of impact, there's only one way, one direction for an impulse to be generated between the 2 objects. And that's going to be along the line that connects these 2 objects. That connects the center of these 2 objects. Now the reason being is because the tangent line direction that's orthogonal to the line that connects the 2 centers, perpendicular to it, provides no impulse in that direction. It can't. So the impulse must be solely within, or can be solely described within, the line that connects the centers of these 2. And that is the difference vector, delta R. Okay, so again, when they collide, just to be clear about what I'm saying here, there has to be an impulse, and an impulse has direction. Remember, impulse is a force times the change in time of the impact. But the change in time has no bearing on the direction of the impulse, just the direction of the force provides the direction of the impulse itself, and the direction of the force can only be perpendicular to the point of impact here. There can be no, or I'm sorry, normal to the tangent line. So the impulse can only be applied normal to the tangent line at the point of impact, which is along the direction delta R. So just to repeat, the impulse can only be directed along the the normal to the tangent line at the point of impact. There will be no impulse along the tangent line. So what that means is that the momentum in that direction will go unchanged for each particle, and the only change in momentum will occur along the line that is normal to the tangent line between these two objects. So basically what that means is if we rotate our coordinate system so that this is the x direction, x prime, and this is y prime, the components in the y prime direction will remain unchanged, but the components in the x prime direction will change according to the case for the one-dimensional impact, the one-dimensional collision that we solved previously. So this can be reduced down to a one-dimension problem if we orient our coordinate system appropriately. And again, that means we have to orient it along the line that connects the center of the two objects, which is delta r. And delta r, well, just show you how to get this. R1 plus delta r is equal to R2. So if I go from R1 plus delta r, I get to the same point as I would if I just followed R2. And so that means delta r is just equal to R2 minus R1. So it's a vector as well. It has direction, which means there's some delta r x in the I and some delta r y in the j. And that delta r x is just the difference in the x components, and delta r y is just the difference in the y components. Okay. Again, we can formally arrive at that by plugging in R2 and R1 as I previously described them. R1 is equal to x1 I hat plus y1 j hat, and R2 is equal to x2 I hat plus y2 j hat. So now we have a vector that points in the direction of the line that joins the two centers of our circles at the point of impact. Now, what we're interested in is this angle. So if we have delta r what I want is this angle right here, theta, because then I can rotate the velocity vectors with respect to that angle theta and solve a 1D collision problem in the x direction while the components in the y direction for the velocity remain unchanged. Okay, so I'm looking for theta so I can rotate my velocity vectors, the initial velocity vector for particle 1 and the initial velocity vector for particle 2 with respect to this line, this new coordinate system, and then I can solve it because then it reduces down to the 1D case along that line, and the components in the y prime direction will remain unchanged. Okay. So I also have delta rx, delta ry. Now, one way to do it is to look at the cosine of theta, which is equal to delta Rx over the magnitude of delta R. I'll write that now as the magnitude. The adjacent over the hypotenuse. What I like to do is basically find, because we're only interested in direction here, and it's basically the same thing anyway. So what I do is I find the unit vector that points in the delta R direction. And so the unit vector, delta R hat, let's call it, is equal to delta R divided by the magnitude of delta R. And so that will give us a unit vector where the cosine of theta is the I hat component and the sine of theta is the j hat component. So it's basically the exact same thing, delta Rx over delta R at the end of the day. And then all you have to do, since R1 and R2 are known, this is basically just the cosine of theta is equal to, now the delta Rx component, delta Rx is x2 minus x1, and that's divided by the magnitude of our difference vector here, the difference in position. And so that would be x2 minus x1 squared plus y2 minus y1 squared, and we take the square root of that whole thing right there. Now all these are known. And so the inverse cosine, the arc cosine of this quantity will give us theta. And then we'll know how to rotate. We'll know the angle to rotate our velocity vectors so that we can reduce our problem down to the one-dimensional case. Now again, just to reiterate, once we find the angle, we can then rotate our velocity vectors with respect to that angle and reduce down to the one-dimensional case. Now let's be careful here because we could run into a problem when it comes to the correct direction to rotate our coordinate system. Since cosine of theta is symmetric, this will give us the same inverse cosine as this. So we'll have to use the y component to determine whether or not it was a positive rotation or a negative rotation. So if the y component's positive, then we have a positive rotation. If the y component's negative, then we have to rotate it according to negative theta. So after we solve for theta, after we get the arc cosine of theta, so once we have theta, it's going to be some positive number, okay? The arc cosine of this quantity will give us a theta that's always going to be positive. So how do we, regardless of what the orientation is? So the way that we're going to define the orientation, or find out what the orientation is by looking at the y component. And if it's negative, then we know that the orientation is a negative theta rotation. And if it's positive, then we know it's a positive theta rotation. So theta is always going to be positive. Theta is always positive after taking the arc cosine of this quantity. So we have to examine delta Ry, or the sine of delta Ry. If it's positive, then we have a positive rotation, positive theta. And if it's negative, then we have a negative rotation, or negative theta. So we'll have to rotate our coordinate system in the positive direction or the negative direction, depending on what the sine of Ry is. Okay. So, how do we rotate? Well, we just have to use our rotation matrix, and we can go ahead and derive that again. All right, so let's go ahead and derive our rotation matrix that we need. So first, we have some vector and I'm just going to call it V, that we can describe in our coordinate system, our original coordinate system, with some theta. Let's call it theta naught. Okay. So we have that x is equal to the magnitude of v, which I'll just call v, times cosine of theta naught, and y is equal to v times the sine of theta naught. And so what we want to do is we want to rotate our coordinate system and describe that vector according to this new rotated coordinate system. Okay, and we're going to call this x prime and y prime. And let's label our angles here. So we rotate our coordinate system by some theta. And now the angle between the new coordinate system and the vector v we'll just call phi. Okay, so now we want to describe our vector according to our new coordinate system. We describe it with respect to the angle phi. So x prime is equal to v times the cosine of phi, and y prime is equal to v times the sine of phi. Now we want to write the equation for our angles, the relationship between them. So we have that theta plus phi is equal to theta naught. So theta plus phi is equal to theta naught. So solving for phi, we have that phi is equal to theta naught minus theta, our angle of rotation. Plugging that in here, we have v times the cosine theta naught minus theta, and v times the sine theta naught minus theta. And now just using these identities, that the sine of alpha plus or minus beta is equal to the sine of alpha cosine of beta plus or minus the sine of beta times the cosine of alpha, and the cosine of alpha plus or minus beta is equal to the cosine of alpha cosine beta minus plus sine alpha sine beta. So we apply these identities, and we get that x prime is equal to v times the cosine theta naught times the cosine of theta. Now since it's minus, we're going to have plus sine theta naught sine theta. Distributing through our v, we have v cosine theta naught cosine theta plus v sine theta naught sine theta, and now v cosine theta is just x. So this is x cosine theta plus, and v sine theta is just y. So y sine theta. Now again, we know these two, x and y, and we know the angle theta naught. And we choose our theta, or the angle of rotation. So x prime now described in our rotated coordinate system for this vector. So the x component of this vector in the new coordinate system, the rotated coordinate system, is described by this expression. And for y prime, we do the same thing, and we utilize the trigonometric identity for sine. So y prime is equal to v times sine theta naught cosine theta. And since it's minus, it'll be a minus sine. Well, let me write the cosine first. Cosine of theta naught times sine of theta. And now again we distribute through. And v sine theta is y, so this is y cosine theta minus x sine theta, which we can rewrite as minus x sine theta plus y cosine theta, just to have our x and y's. And in order. Okay, so that's how we would transform our vector v into the new coordinate system and gather its components. Now we can write this in matrix form, where we have that to this rotational rotation matrix that we can write now as cosine theta, sine theta, and minus sine theta, cosine theta. We can multiply that by our vector xy. So that's it in a nutshell. So that's how we would transform our vector. And that's our rotation matrix. Cosine theta, sine theta, negative sine theta, cosine theta. And if we multiply this matrix by this matrix, we'll get cosine theta, x times cosine theta plus y times sine theta. And that's equal to x prime. And we'll have negative x sine theta plus y cosine theta, which is equal to y prime. So that's the rotation matrix that we're going to have to utilize twice, because we're going to rotate this into the coordinate system that will isolate the impulse along the x direction, and there will be absolutely no impulse along the y direction. So once we transform our velocity vectors, our final velocity vectors, in the new coordinate system, we can eliminate one component, because the component that is tangent to the line of rotation, or the line that intersects the center of our two circles, will remain unchanged. So the initial velocity along the tangent line will remain unchanged. So the final velocity will be equal to the initial velocity along the tangent line, because there is no impulse provided during the collision along that line. And the impulse will solely be along the x prime direction. Now this is another important aspect, this is assuming either a frictionless surface or well, yes, it's assuming a frictionless surface and no rotation. So they would just collide at a single point, and the entire impulse during that collision will be directed along the x prime direction. And so now we can reduce our two-dimensional collision to a one-dimensional collision along the x prime direction, and the initial velocity along the y prime direction will remain unchanged. So then we can solve for the final velocities along the x prime, and once we have the final velocities along the x prime, we'll have to rotate back to our original coordinate system, so that'll just be a rotation of minus theta, and we will have the new final velocities that we were solving for. So let's go ahead and go through each one of those steps, just to be very clear about how we get from point A to point B. We have all the pieces that we need now to put the entire algorithm together. Okay, so let's go ahead and recap everything that we've done so far and put together the full solution for our two-dimensional elastic collision problem, the full algorithm. So let's go ahead and start from top. Okay, so let's start by listing our knowns again. Our knowns are R1. We know the X and Y coordinates for R1, R2. And we know the initial velocity. For particle 1 and particle 2. So v1 I x plus v1 I y. And the initial velocity for particle 2. And we know the mass is m1 and m2. So those are our knowns. And our unknowns or the variables we're solving for are our final velocities, that's v1fx and the I hat, v1fy and the j hat, and v2f, these two components, v2f x and the I hat, and v2fy in the j hat. And so these are our four unknowns. Okay. So the first step was to find our difference vector, difference in position. Which is equal to x2 minus x1, the I hat, plus y2 minus y1, the j hat, I'll call this delta rx, this delta ry. And so now what we're looking for, again, is the angle. And if you recall, I'll just go ahead and write it down. The angle that we need to rotate our coordinate system is going to be defined as the arc cosine. And I'm just going to write this in terms of deltas. So delta Rx over the square root of delta Rx squared plus delta Ry squared. But remember, the sign is important here. So what I'm going to do is I'm going to include the sine function. And now the sine function is equal to +1 if x is greater than 0, 0 if x is equal to 0, and negative 1 if x is less than 0. Okay. Just a little reminder of how the sine function operates. So I'm going to incorporate it. Remember, we are interested in the sine of delta Ry, so to write theta down as a complete function, utilizing the sine function, it's going to be the sine of delta Ry times the inverse cosine delta Rx over delta Rx squared plus delta Ry squared square root. And so this is how we will calculate our proper angle of rotation. Okay, so that's rotation angle. And then once we're done with that step, we rotate with respect to the velocity vectors. Well, we rotate our velocity vectors with respect to the new coordinate system, the primed coordinate system, excuse me. So we rotate our coordinate system by theta. And so this, then we can write down as V1 Ix prime, sorry, V1F x prime, V1F y prime is equal to cosine of theta times the sine of theta, or sorry, cosine of theta as our first element in our matrix, sine of theta, that's the second element in the first row, then minus sine of theta, cosine of theta. These are matrices. And then we have V1 fx, V1 fy. So this will describe our final velocities in the rotated coordinate system, and our initial velocities will be described in the same way. V1 y prime. Now we really won't use this top equation. We'll use this bottom equation, and then we'll use the reverse operation to get back to the original system. So again, cosine theta, sine theta, sine theta, cosine theta. Okay, so this will give us our velocities with respect to the primed coordinate system. So we have our initial velocity, with respect to the primed coordinate system. Now, of course, the reason we did this, just to remind you, is because the impulse can only be directed along the x prime direction and not the y prime direction. So the velocities along the y prime direction will remain unchanged. So what that means is that v1 fy prime is going to be equal to v1 I prime y prime. So I've only rotated the first velocity here, the velocity for the first particle, and not the second particle, but we basically do the exact same thing for the second particle. And then we can write down that v2 f y prime is equal to v2 I y prime. So the velocities along the y prime direction remain unchanged. All right, so now all we have to do step number 3 is solve the 1D collision problem for the x prime direction. And that will give us v1 f x prime and and v2 f x prime. So now we have v1 f y prime, v2 f y prime. They're just equal to the initial velocities in the y prime direction. And now we can solve the 1D collision problem for the x prime direction. We can get v1 fx prime and v2 fx prime. So now we have all our final velocity components. However, they're in the primed coordinate system. So step number 4 would be to rotate back to the unprimed coordinate system by what I'm going to call it theta prime, which is just equal to negative theta. And then that will give us our v1 fx, v1 fy, and our v2 fx, and our v2 fy. Solved. So again, I was just going over the algorithm. So those 4 steps will get us there. Find our angle, rotation angle, rotate our initial velocities according to the primed coordinate system. And then just solve the 1D case for the x prime direction. It just reduces down to that, and the velocities remain unchanged in the y prime direction, and then we rotate back to the unprimed coordinate system. And that's it.